Yeah, that's too much room. How am I feeling it? A hollow aluminum cylinder 20 centimeters deep has an internal capacity of 2 liters at 20 degrees Celsius. Is completely filled with turpentine at 20 degrees Celsius. The turpentine and the aluminum cylinder are then slowly warmed to 80 degrees Celsius. So you got a container holding turpentine, it's heated, right? How much turpentine overflows? Because what happens? We're doing volume expansion, right? And let's look up our numbers. We need a couple numbers here. So I gotta go back. We'll come back to the problem. This is number 19. We gotta go back here and find the numbers. We need what? What's the container made of?
Aluminum.
Where's the table? Okay, we need aluminum and turpentine. So alpha of aluminum is what? 24 times 10 to the minus 6. And we need beta of turpentine. Beta, remember, is volume coefficient. Turpentine is 9 times 10 to the minus 4. Okay. This is a good problem. All right, now I go back to the problem, which was number 9.
19.
19. Okay. And I have the numbers up there for you. So you have a container filled with turpentine, right? And then you heat it, what happens? When you heat something, what happens to it? Temperature goes up, it expands. And you can see the turpentine is going to expand more than the aluminum, right? So it's going to overflow. That's what you're looking for. How much overflow there is. So the container is going to get bigger. And the turpentine is going to get bigger. Right? It's going to be over. This is what we're looking for. The overflow. Make sense to you guys? Remember, anybody remember the formula for volume expansion?
Final length equals to initial length, open parenthesis, 1 plus alpha delta t. Well, 3 alpha.
3 alpha, right?
Yeah, it should.
Because it's volume or beta, right? Anybody remember that? Area is 2 alpha, linear is 1 alpha, volume is 3 alpha. Is that the test form you're gonna fill out?
Yeah,
Okay. We're gonna do that.
I feel like most fits this year.
You mean just to sign it? 2 weeks. Today the 9th.
It's the 10th. Please don't worry.
Why do we use the 20 centimeters deep?
Part C.
Oh,
Let me get some new tissue. I'll be right back from the restroom. You already know, got a formula for how to find this? An idea?
yeah.
Right, we're looking for this section here. Just this.
Yeah.
Right, everybody see that? I think that's what I'm looking for, right? The difference between the final turpentine and the final aluminum. I'll give you the other stuff. You see that, Mary? So this would be B naught 1 plus beta turpentine delta T minus B naught 1 plus 3 alpha delta T. All right, everybody see how I did that? Yes?
So the only reason we're using that alpha is because it's what's given to us. Like we're given the
Right.
linear expansion aluminum.
Yeah, when you look up solids, they always give linear.
Okay.
So, but you're doing a container, so you gotta multiply by 3. Exactly. So you multiply this out, the B naughts will cancel. You end up with a B naught beta T minus 3 alpha delta T. That's what you'll end up with. Right? Put in your numbers. 9 times 7 minus 4. Minus 3 times 24 times 7 minus 6. Times delta T, I think it's 60, isn't it?
60.
All right, what did you get?
I got 0.1.
Anybody else?
Uh,
Did you get that?
I got way lower.
What did you get?
2.0000001.1837.
That doesn't sound right.
Let me double check.
I didn't do it the way you did though.
0.994 milliliters,
0.1.
which is 0.1 liter, right? Or is it 0.01 liter?
No. Milliliters is less than
1,000, right? So there's 1,000 milliliters is a liter.
Yeah, I got 0.107999.
with what Dr. Brown did.
With what I did.
Because if I want to go to liters, I got to move it how many places? 3, right? Oh, it should be 0.01 liter, is it? Or is it 0.1 liter?
I don't know, I didn't do it the way you did. Maybe wrong.
What'd you do?
No, it'd be 0.099, so basically 0.1.
0.1? I was having conversion problems here in my head. 0.1. 0.099. Oh yeah, right. 4. I don't know why they convert to milliliters on you. But whatever. This should do it. Pretty sure. Did that do it, Sarah?
Yeah.
Sarah says it works. Okay. What is the value of the turpentine remaining in the cylinder at 80 degrees Celsius? How do I get that? I want to know how much is in here, inside. Because it's filled with turpentine. So how much turpentine do I have left?
You just calculate the linear expansion and then subtract the initial volume.
Why would we just
Alright.
find the volume expansion of the cylinder? The container, right? And that'll be what's left. That's how much I'm holding. Does that make sense, everybody?
Mm-hmm.
So that's just this term. V naught 1 plus 3 alpha delta t. We just put in that. And so it's 2, 1 plus 3 times 24 times 10 to the minus 6 times 60. What did you get?
2.00.
0.
2.009?
Yeah.
2.01?
Yeah.
No, count it. That's what I thought. They were on 2 digits. Okay. This part's B. Now part C, we gotta use the 20%. Or 20 centimeters. If the combination with this amount of turpentine is then cooled back to 20 degrees Celsius, so not the overflow, just this is cooled back, now how far below does it sit? We want to see how far deep, right? Because now when it cools, it's going to be less. So, okay. So, how do you do that? We got to cool my turpentine back down, right? And find the new value of it. So, what's my formula here? Right? What's my V naught though now? It's not 2, it's what? 2.01, because I'm starting with a bigger container. Beta is 9 times 10 to the minus 4. What's my delta T now? -60, right? So those are the things you gotta catch. The new value, the temperature change is minus. V final equals what? Anybody? What did you get, Sarah?
No.
What did you get?
1.9.
1.9? It's less than 2, so that's good, right? 1.9 liters. That's how much turpentine I have. Right? 1.9 liters, the container's 2. We gotta figure out delta Y. So how are we gonna do that?
Oh, they told us how
They told us how deep.
deep it was.
Yeah, 20 centimeters. And how do we get value?
It's proportional, right?
It's
so
proportional.
You could say like 20 centimeters equals 2 liters.
Yeah, because they both have the same area, so it's proportional. So that means this is 20, 1.9, right? we just take the ratio of the volumes. So 1.9 divided by 2 equals, that gives me my percentage, which is what?
0.95.
0.95?
Wait, might not be that. I think it is.
Yeah, I think it is. So, this is 95%. So this is 5%, right, to get 100?
19 centimeters.
So what's 5% of 20? 1, right? I think it's 1 centimeter below, because you have 19 centimeters full. 0.998.
Oh, you were wrong. You should have known that.
1 centimeter.
Oh, yeah.
Right now it has to 1, doesn't it?
Yeah, because it's the amount.
Why is there no 3 in the second, or in that volume final? For the
No.
one up there.
Because I'm doing turpentine, so it's just beta. Because it's a liquid.
Okay, yeah.
Right? I use the 3 when I have a solid, because they give me alpha. Alright, so you're going to have some kind of expansion on your test, for sure. Certainly. Let's try another kind of problem. Let's see. Think we're gonna have any more from this chapter? Because I'm not gonna ask you kinetic theory of problems on gas. So. Did we do this one already?
I think so.
I think so too. See, that was one where I had to do it in a row. But it wasn't bad. Oh, we could try this one. It doesn't have answers, but.
That's already just.
What was that?
It's already.
Oh, it was on your homework? Oh, okay. Okay, let's try some. Alright, let's try 31. This should be pretty easy plug and charge, right? Oh, I'm sneezing. And I know guys what I said. There you have it, Calvin. Here goes isobaric expansion to 2.5 kilopascals. Oh, at 2.5 kilopascals. If the volume increases from 1 to 3, and 12.5 kilojoules is transferred to the gas by heat, what are the change in the internal energy and its final temperature? So this is the kind of thing where you're going to have to know the process and from that be able to calculate stuff. Right? Does that make sense, everybody? You should draw the PV diagram for it too, so you know what you're looking at. So isobaric, what's that mean? Pressure is constant. And that looks like that, right?
Yep.
E naught. E naught. Final. think that's what it is, right? Which one are we gonna use? Anybody got it?
U equals to Q plus W.
Okay, U equals Q plus W.
Isn't it the first law of thermodynamics?
Yep. Delta U actually. Right. Change. Yeah, just U. Delta U.
Mm.
Okay, so we need that. We got Q. Can we find W?
Yep.
Anybody else?
No.
Jared, how would I find W?
Um,
Ooh, Matthew's gonna steal it. Matthew for the steal.
negative
And
P
if-
delta V.
Oh, he lied. Sorry about it, Jared.
That's
Minus P delta V, right? Does everybody see that? And because this is a rectangle, right? It's just area. If it was isothermal, I'd have to use the natural log, right? Use the calculus. So this is easy. So this is Q minus P delta V. So that gives me delta U. Let's just plug in. Q is what? 12.5 times 10 to the 3 minus P, which is 2.5 times 10 to the 3 plus 3 minus 1, right? So yeah, 12.5 times 10 to the 3 minus, what's 2.5 times 2? 5?
5. 10 to the 3.
So 12.5 minus 5 gives me, is that 6.5?
Yeah. No,
Times 10 to the
it's 7.
7.5? My head's all stuffy. Kilojoules. Everybody see how I did that? Mary, you with me?
Yeah.
You look like you don't like it.
I have something wrong, I think.
Oh, okay.
It was just like.
Can I get the final temperature?
Yes.
Yeah, what formula?
Why are they times 10 to the 3rd?
The kilojoules, kilopascals.
I used like the proportional relationship between temperature and volume because it's like constant pressure.
Okay.
So you can set those.
So you use PV equals
NRT.
nRT.
And then divide those things by P and T.
So use that relationship, right? Nope.
No.
No,
divided
V's
this-
changing.
I got like the P under the N and the R and the
Yeah.
T under the V.
So V over T. That's what you use.
So V naught over T naught equals V final over T final.
Yeah, that should work. That's not gonna give me delta U. That'll give me T final.
Oh, I'm sorry, I thought it was,
Yeah, that's the next question.
oh, final temperature, right?
That should work.
Yeah.
You could also use what? And
CV delta T.
CV. Oh, but they don't give it N, do they?
Yeah.
Actually, CP delta T, isn't it?
Yeah.
Yeah, yeah, cause it's,
Yeah, I saw you use this because they didn't give me N. I knew N, but you don't know N.
Is CP the 5 hertz?
yeah.
Yeah, 500 R.
You're not gonna give us any like diatomic anything on that.
No, I don't feel. I might ask, good concept question, what's the difference between polyatomic,
That's great
diatomic?
concept questions. What are
Yeah.
you thinking for those?
Wait, you said,
Diatomic and polyatomic.
Yeah, the
said
difference.
entropy,
Entropy,
and then,
heat transfer,
like convection.
conduction, radiation.
Radiation.
So T final's what?
It was 900, I think,
Yeah, so
unless I did algebra very wrong.
T final over V naught times T naught, right?
T not.
3 over 1 times 300. Should be 900. Is that what you got?
Yeah, again, my algebra could be wrong.
Mine too, I'm all stuffed, so it's just like, ah,
I'm just,
makes me tired. You're either gonna have some kind of gas process, right? Isothermal, adiabatic, could be any of these. Let's find adiabatic, because I love adiabatic.
Are you thinking about efficiency as well? Carnot engine?
Yeah, the efficiency of Carnot engine, that could be on there.
so like something like, you know, like calculating the efficiency?
Yeah, so you got two temperatures, what's the efficiency, how much work is deposited, that kind of thing.
So like use those different formulas?
Yeah, you use
did,
both
the
those
key
formulas, put them together.
Yeah, okay, that makes sense.
Here's an isothermal, we could try that, that's pretty easy.
I like isothermal.
2 mole sample of helium, monatomic helium is. That's why they told you it's helium. Initially at 300 calories, 1.4 ATM is compressed to isothermally to 1.2 ATM. Noting that the helium behaves as an ideal gas. Fine, the volume of the final volume of the gas, the work done on the gas, and the energy transferred by heat. And we might need the ATM conversion. So let's put it there.
It's,
It's 101, right?
101,325. Pascals.
I lost my blue marker. Done enough homework with it.
Yeah.
101, 3 something?
325.
Pascals. Or we can write this as 1.01325 times 10 to the 5, right? 1, 2, 3, 4, 5. Or we can write it as 101.325 kilopascals. They're all to differently writing Pascal. So the full thing, power, right, scientific, or kilopascal. Okay, try this one. Isothermal. What's that mean?
Constant temperature.
Constant temperature. All right, give it a try. We're going that way, right? We're compressing the gas. So the pressure is going up. P naught is 0.4. final is 1.2 ATMs, is that right? This should be pretty straightforward. We got a couple minutes here left. What's our formula? PV equals nRT, right? We need that.
What's R again?
The gas constant, 8.314 or something.
You're gonna give that, right?
Yeah, I'll give you the gas constant. You remember what the value is?
8.314.
Is it 8.314? I remember it was 8.314 or 8.134.
Oh, R?
Yes.
8.314.
That's like joules per mole
Kelvin?
Kelvin, yeah. Because we just gotta solve for V, right? For V final? That's easy. V final equals nR T final over P final. The only thing is I gotta put it in
Pascal.
Pascal, right? Because ATMs, that doesn't work. Right, this is SI units. So 2 times 8.314 times 300, I think, divided by 1.2 times the conversion, 101. 0.325 times 10 to the 3 per kilopascal, right? That should give it to you. How much work? The work done on the gas. How do I find the work?
It's the negative of Q.
Okay.
And Q would be, you could just use like the traditional, like, no, because
It's isothermal, so I have to use
Natural log.
the natural log. Yeah, if you forget, you can derive it, but the work is minus nRT ln V final over V initial. Right? And if you forget, you can derive it. We derived it in class. Using calculus. Okay, so why don't we put that? That's easy, right? Minus 2 times 8.314 times 300 times the natural log V final over V initial. Now that I can leave, can't I? In ATMs? Because they'll cancel. So it's 1.2 divided by...
Wait, those are the pressures?
Those are
Oh, those are
volume.
pressures. Ah, nuts.
So we would have.
I gotta get V final.
We would have calculated V final.
I got V final. I gotta get V initial.
The initial.
Well, how do I get V initial?
Same formula. PV and RT.
Divided by... Is it 0.4? No? It should be 3 times, right? The only difference is a factor of 3, isn't it? So what do we get? And then you just take those. Anybody get V final for us? Or V initial?
Are the moles always constant?
Usually.
Usually. We assume so, right?
Yeah. I mean, not always. Like, okay, weird stuff.
Yeah, like 0.123
Yeah. 0.123.
initial, yeah.
So then I would take V final,
We didn't calculate that.
0.041, right?
Mm-hmm.
Oh, yeah, sorry.
divided by 0.123. It's 3 times. Yeah, so that makes sense. There's a factor of 3. That's going to give me a minus to cancel that minus. So this will be positive. So 5.84 kilojoules. Should come out, right?
Delta U is gonna be 0 for this case, right?
Yeah, delta U is 0. Right? So that means the work, the heat is equal to what? Part C. Mary already told us. So if the work is positive, the heat should be negative.
So the isothermal, the change in U, the change in the internal energy is 0.
Yeah, not U.
There's
There's internal energy, yes.
still internal energy.
The change.
And for that, you would just use like the value for temperature, and that
Yeah.
would give you like the
Right.
internal.
How do you compute internal energy again?
U, just to compute the energy, U is 3/2 nRT or 3/2 nKT, right? That's U. Delta U is what's in the first law.
Awesome. And that is to compute U for any kind of process, right? Like adiabatic,
Yeah, and that's all for isothermal.
isothermal.
So yeah, it'd be different for polyatomic stuff, but. We're gonna do all isothermal. So speaking of N not changing, think about what happens when you heat a room. Like this room here.
Mm-hmm.
So what's constant in this room? Not what's fixed?
Pressure.
Volume.
Pressure and volume. The temperature and the number of molecules change. So if I heat this room, if you look at the ideal gas law, PV equals nRT. What changes? N and T, right? So that means N naught, T naught equals N final, T final. So if I increase the temperature in the room, what happens to N final?
Decrease.
It goes down. So I push molecules out of the room. Okay, here's an interesting question. What happens to the entropy in the room?
Stays the same.
No, it's gonna increase.
No and no.
Decreases.
It decreases.
Decreases.
Because if you look, entropy is proportional to the number of molecules in the room, and everything else is a log. So it is a strong dependence on the number of molecules. So as you change the molecule, if you take out molecules, you way decrease the entropy. I still increase the entropy of the universe because I put more molecules out there in the environment. But don't you think if you heat something, you increase its entropy? But that's under fixed number of molecules. But here I have variable number of molecules. So it's a little different effect.
But this is all like ideal gases, which in reality
Yeah.
don't really
Well,
exist. Like,
yeah, so, but this would be pretty close.
Yeah, I was just reading through all those conditions and.
Yeah, if,
wow,
here I'll show you, like,
that's shocking.
we have time, well, kind of. Gas.
Like assume the dog is a square. You know?
Let's see, no, I want gas law or Vander. So this is it. So this is, can you see that?
Yeah.
Here, you're taking into account intermolecular forces and the volume of the molecules. And that's determined by these constants A and B. So A deals with the intermolecular forces, B deals with the size of the molecule. So this is a variation called Van der Waals equation. So this is, more exact.
That actually represents reality, right?
This is closer to reality because I'm worrying about intermolecular forces and the size of the molecule.
But we don't study that as an undergrad, right?
No.
No. Not even the physics major?
We might look at it in the thermal class.
Oh, so we're gonna have that, right? Like
Yeah.
engineering.
Yeah, so, but it wouldn't be the only thing. Yeah, you probably look at it, see how it works.
I will say I have thermal written down for spring of junior year.
Okay. See if that fits.
It's like an as needed class.
A what?
It's like an as needed class.
Yeah. Yeah, because no one's ever needed it. Yeah.
Can I cut the recording?
Yes.
Okay.
So just to give you an
Thank
insight,
you.
there's other versions.